And it's not about the dog. Got it. So it's not about the dog. And the interesting thing was Pluto and the dog were named about the same time, but there's no real evidence of any strong link. And the only thing we can say is that Pluto sounded quite catchy, and the Disney animators thought it sounded better than Rover. It's a catchy name, or a cuddly name. So let's start off with, we know there are 5 naked eye planets in the solar system. Then we had the first telescopic discovery of Uranus in 1781 by William Herschel. And then when people started studying the orbit of Uranus, they felt it wasn't a pure orbit and it was being perturbed by something else, which they thought was another planet. Calculation released in 1846 of a position of this suspected new planet by the French mathematician Leverrier. And this was a brilliant piece of mathematics, it really was. The next night, Neptune was immediately discovered. So this was really spot on work. There is still debate about the orbit and the possibility of another planet, Planet X. But as we'll see, this really came about because of not long enough to work out the orbits, and also just actually errors in the calculation of the orbits. So Pluto comes along next, and Pluto was being searched for by Percival Lowell. He searched for this Planet X from 1906 until he died in 1915. Then there was a legal impasse whereby his wife, Constance, couldn't get hold of the data, and the observatory held onto it. But eventually the legal impasse was broken, and she got access to all the data. And so the research resumed again in 1929. A young astronomer called Clyde Tombaugh, an astronomer and engineer, and he used a cunning device called a blink comparator, which I'll explain in a moment. And in January and February 1930, he discovered Planet X, which subsequently became known as Pluto. And there's always a question, was this just by chance? And in fact, Pluto had been observed before, but not recognized as a planetary body. So this is Clyde with his own Newtonian telescope. This is not what was used to find Pluto, but it's a nice, I think it's a nice image of the young Clyde with his amateur telescope. This is the blink comparator, and it works brilliantly. And it's really good for finding things that have moved in the sky or changes of brightness in different times. And so there are locations on here where you put a photographic plate, then exactly the same image at a later time on the second one here. And there's a device which flicks between them. So you put your eye to this eyepiece here, and the device flicks between the two, and the brain is very, very good at recording differences. And so here is the discovery image. And this works really, really well in Zoom. So I apologize to the people in the hall because I'm sure you're going to struggle to see this. If you look at the little arrow over here and you see this little tiny dot, there's a nice little triangle here, which is a good memory one, but little dot here, this is on January the 23rd. And then 6 nights later, here we have the same little triangle, but the star that was there, or the object was there, is gone. And there's a new object appeared over here. This was the discovery of Pluto. So I said, this works really well on Zoom, but not so well in live audiences, as it turns out. And as I pointed out, Pluto had actually been recorded before, but not identified or recognized as a new object on a planet. So now we come to the naming of Pluto, which was really quite interesting. At that particular time, the Lowell Observatory had the naming rights. And so they had 1,100 suggestions, and this came down to a short list of 3 names for an internal staff vote. They were Minerva, Kronos, and Pluto. Now, Pluto, interesting enough, was proposed by an English 11-year-old schoolgirl from Oxford, Venetia Burney, and she was keen on astronomy, and she'd heard about this, and so she passed the name on to her grandfather, who passed the name on to the physics director, head of department, who then pointed out the Lowell Observatory. And lo and behold, Pluto was a unanimous choice. And Pluto is god of the underworld, which people seem to ignore, but it just has a nice catchy sounding name. It's also maybe because PL in the beginning of Pluto sounds like Percival Lowell from the Lowell Observatory. So there's also a little bit of sort of emotion into that as well. And interesting, once Pluto was named, then the tradition of naming new elements was continued, because uranium had been named 8 years after Uranus had been discovered. And then we had in 1940 Neptune with Neptunium, and now we had in Pluto, and then we had in 1941 plutonium. So this is a nice little link between physics and astronomy. So now let's have a look about Pluto. We've discovered it's there, but what do we know about it? And the key parameters for any body that you want to look at: size, mass, and orbit, certainly for a body in the solar system. So let's start off with the mass. Okay, so you can work out the mass by its effect on the orbit of Neptune and Uranus. And if it was having the big perturbing effect, in 1931, people calculated it was around the Earth mass. In 1948, Gerard Kuiper, he sort of guesstimated the diameter and then worked out the mass, and he came out with about 10% of the Earth mass. So Pluto is shrinking. In 1976, Dale Cruikshank from the University of Hawaii, he measured the albedo, the reflectivity of Pluto, and he found it was composed of methane ice on the surface. So this meant it was very bright and very shiny, which meant actually it was only less massive. So the mass went down to 1% of the Earth. It's not going good well for Pluto here, is it? And then in 1978, discovery of Pluto's moon Charon, and the subsequent orbit then gave 0.02% of the Earth. And so Pluto is definitely very, very light, and this immediately casts doubts about whether Pluto could possibly be Planet X, and in that sense, it's no way it could perturb the orbits of Uranus, Neptune and Uranus. And if you look at this graph, which on the y-axis plots Pluto's estimated mass in Earth masses, started off in the olden days at 10, and by the time of the discovery, it had gone down to about 1 in here. This is the point. And then if you look how it just cascades down to almost 0. And in fact, Pluto should almost have vanished by now if you look at that graph and predict what's going to happen. And of course, with better calculation of orbits, Pluto was discovered to be really not needed at all in terms of that. And that was because people had much longer times to work out the orbits of Uranus and Neptune, because these are distant bodies and therefore they don't move very far in the sky. So they didn't have much of an orbital distance to essentially extrapolate to a full orbit. And so better calculation of orbits, essentially Pluto, or the discovery reason for Pluto, just goes away entirely. So now we've diminished Pluto in terms of its mass. What about Pluto's size? Well, this is very difficult to determine. It's too small to measure directly until very recently. And it's about 0.1 arc-second of arc. If you want it, and from the Earth, that's about what it is. And you can make estimates, but you've got 3 parameters of albedo, which you can make a reasonable guess at, but then you've got to get the density of the planet. That's assuming you know the mass, then you've got to guess what the density is. So you can make estimates, but it's tricky. The best estimate is now 2,374 kilometers from direct measurements of the New Horizons missions, which we'll talk about at the very end. Now, 2,374 kilometers is very, very small compared to the other planets. And how small is it? It's really, really very small. So this is the Earth, this is our moon, this is poor old Pluto. So Pluto is significantly smaller than the moon. And in fact, if you take on the Galilean satellites of Ganymede, Callisto, Io, and Europa, and then Saturn's moon Titan and Neptune's Triton, Pluto really ends up as being a little minion altogether. And this was meant to be a planet. So immediately as its size and mass became pronounced, people started querying, was it a planet? Well, what about its orbit? We haven't mentioned that yet. We've mentioned the fact it's not very massive and it's small, but what about its orbit? Well, its semi-major axis is about 40 astronomical units, so it's beyond Neptune. Orbital period of 248 years, which is very extensive. But the really key difference is the eccentricity of 0.25. And essentially all the other planets have essentially circular orbits to a really high approximation. They're circular orbits. But Pluto has a distinct eccentricity of 0.25. And the inclination of the orbit to the ecliptic is 17 degrees, whereas everything else sits within 2 degrees and essentially a flat plane. So Pluto stands out as being different from the rest of the planets. And this gives you a pictorial example of where you have the planets essentially, and Pluto with a really quite a highly elongated and inclined orbit. So then we ask, well, is there anything else that we know of which have similar orbits to Pluto's? And the answer is yes, we do know. The Kuiper-Edgeworth belt discovered by Kuiper in 43 and Edgeworth in 51, a regime of small bodies way out in distance part of the solar system, a reservoir perhaps for comets or centaurs, which we'll talk about soon. And then in 1992 was a big breakthrough. Discovery of the first Kuiper belt object, which we'll call KBO from now on, by Dave Jewett and Jane Liu of the University of Hawaii, and this is called Albion. And so now we had a new body, and you can work out essentially its orbits. There's now more than 3,000 of Kuiper belt objects discovered, and this is just the tip of the iceberg. There's no doubt about it whatsoever. Kuiper belt objects come in various forms, and astronomers love classifying these, and I won't spend much time on this. Cold, circular, non-inclined orbits looking like planets. Hot, elliptical and inclined orbits like Pluto. Resonance, orbit looking with Neptune. And in fact, Pluto has 3-2 orbital resonance looking with Neptune, and then scattered by Neptune because they get too close to it. Another name for all these things is trans-Neptunian object, which is probably the modern version, but I'll use KBO and TNO interchangeable throughout this talk. Now, here we have a pictorial diagram of the layout of the planets. And here we have Uranus and Neptune, Uranus in green, Neptune in sort of a bluish color. Pluto is in magenta. And you see quite a lot of the KBOs actually don't look too different from Pluto, but then you have other ones, like this one called Eris, which has a very long and inclined orbit. Then we have this one called Sedna, which has a very, very open orbit, essentially. And this other KBO 2012 VP113, which essentially is a hyperbolic orbit. So this is what some of them are meant to look like. And if you see the Hawaiian names in there, Haiyaka and Namaka, this is because many of these were discovered from the University of Hawaii in Honolulu. And so that's why you get many of the names. But you see, I mean, these are all guesstimates, but you can see the sizes are really quite large. And the interesting thing is that Eris, which we'll talk about in a moment, is almost all as big as Pluto. So what's the impact of this? Well, first of all, the discovery of Charon, Pluto's moon in 1978. And Charon is big compared with the size of Pluto. It's certainly bigger than any other moon compared with its parent planet. And as a result of what I've been talking about, by the mid-1990s, the planetary status of Pluto was being questioned, certainly by planetary astronomers. Dave Jewett from the University of Hawaii in particular. And I was stationed in Hawaii at the time as director of JCMT, as mentioned. And Dave Jewett came across and gave a seminar. And it was the first time I'd really got into this in terms of something new going on in the solar system. But at the end of the seminar, I was totally convinced Pluto was a Kuiper belt object. And I just been sold instantly in the space of a 50-minute seminar. And so there was a proposal to the International Astronomical Union in 1999 to reclassify Pluto. But the IAU knew this was far too hot a potato to get hold of, so they ignored that. However, in 2000, the Hayden Planetarium was essentially reorganized in the Rose Center in the American Museum of Natural History in New York. And the director of the planetarium, Neil deGrasse Tyson, who many of you may have seen on television, is a very good communicator on American TV and astronomy. He had the temerity to omit Pluto as a planet, and he only had 8 planets there. And this caused actually a lot of grief. It made the news significantly, and you got a lot of hate mail for this. So this was an omen of what was to come if you started messing out with Pluto. And then in 2003, Eris, who we mentioned previously, was discovered by Mike Brown, the famous solar system astronomer. And this at the time was thought to be bigger than Pluto, and it's certainly around the same size as Pluto. So was this Mike Brown's discovery of the 10th planet in the solar system? And then it got worse in 2003, the same year, when Sedna was discovered, also thought to be about the same size as Pluto. Does this make it Mike Brown's 11th planet? How many more could we then have to that? And this is HST image in 1994 using the faint object camera of essentially Pluto and Charon. And you see Charon is distinctly big compared with Pluto. So we'll talk a little bit more about this. It's a double planet. We'll talk a bit more about this later on. So now let's move on to the International Astronomical Union, because they now come into the scene. After giving up in 1999 and saying, whoa, we're not going to touch this with the barge pole, they then had to eventually do it. And the IAU was founded in 1919, so we've just had the centenary. World's largest professional body for astronomers. It's got about 10,000 members, depending upon how you count them. It has a wonderful mission to promote and safeguard the science of astronomy in all its aspects through international cooperation. Wonderful. It's also the internationally recognized authority for nomenclature, for naming designations to celestial bodies and its surface features. So if you want an asteroid named after you, the IAU will do it or not, as the case may be. Surface features of the moon, Mars, and wherever, they are the authority. What does the IAU do? It does many things, but one of the things it does for astronomers is every 3 years, it holds a mega general assembly. It's some city on the Earth for two weeks. We have the largest, most diverse astronomical meeting and about a variety of topics, and also about principles and philosophy. So this happens every 3 years, and thousands of astronomers go and attend. So Pluto was now a big dilemma, and the IAU agreed that they would have to discuss and debate this in the 2006 General Assembly, which is going to be held in Prague. So in 2004, to be well prepared, the IAU set up a planet definition committee. If in doubt, set up a committee. So a planet definition committee, which will define how you define a planet in the solar system. And I thought, well, how hard can this be? But interestingly enough, the IAU already had a Division 3, one of its subsets. This Division 3 was Planetary System Sciences. And these groups, they definitely had a sway in how you define things in the solar system. And they wanted to have their say, and they'd been totally ignored by the IAU executive. So they were not a happy bunch altogether, given the fact that they thought they were the people who knew best what we were talking about. So the planet definition charge, and I'm going to read through these because it's very interesting to see how you have to define how a defining body would look at essentially a scientific object, an objective. So 1, discussing the broader social implications of any new definition of a planet and recommending a course of action that balances the scientific facts with the need for a social acceptance of any change. 2, addressing the status of Pluto and of the newly discovered TNOs in the light of recommendation 1. 3, considering whether the current naming procedures for planets and minor planets have exacerbated the problem of defining a planet and recommending whether divisions are needed. This is quite a, number 3 there is quite a redefining moment. And 4, attempting to frame these recommendations as a resolution or resolutions that could be put before the Prague General Assembly in August 2006 for possible adoption. So this essentially was where they were in terms of moving forward on Pluto. So how do we go? The president now stepped into the issue and said, and it's actually very important, these words. He says, from time to time, the IAU makes recommendations on issues concerning astronomical matters affecting other sciences or the public. And this is a rarity. It doesn't happen very often at all. Hence, IAU recommendations should rest on well-established scientific facts and have a broad consensus in the astronomical community. And you note these words of broad consensus and well-established scientific facts, which we'll return to later. Now, the answer from the Planet Definition Committee was actually turned out to be really very, very simple. And they got through their work in essentially no time flat. And they said, a planet is a celestial body that A, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium, brackets nearly round shape, and B, is in orbit around a star and is neither a star nor a satellite of a planet. In other words, it's going to be big enough for its own gravity to pull it into a nearly spherical shape. And they said, and that's it, that's the answer. And that brings up lots of interesting things, as we'll see. Now, the IAU knew that this Pluto definition or redefinition or whatever could have a big impact. They were well aware of that. So they appointed a press officer. They'd never had one before, well before the General Assembly, in fact, 6 months beforehand. And it turned out that the press officer was a very good friend of mine. I was president of the Commission 55, Communicating Astronomy with the Public, and he was the secretary. So we worked together very, very well and knew each other very well indeed. And he was excellent press officer. So the executive of the IAU and the executive committee are a bunch of wise men and women, but it's mostly wise men at the time, who essentially put resolutions together for the General Assembly to discuss. And they came up with a proposal of 12 planets with potentially more to come. And they had 8 classical planets that dominate the systems, and that's the normal 8 that we know about. 4 planets in a new and growing category of plutons, i.e. Pluto-like objects, which is Pluto and Charon, the double planet, Eris, the Tycho trans-Neptunian object, and the asteroid Ceres, which is big and actually round. So the General Assembly came on August the 14th to the 25th, and my colleague showed me the press release, which was going to be issued on the Monday, and on the Sunday was the sort of opening day of drinks and chats and things like that. And he came up to me and said, "Look at this, hot off the press. This is the press release for tomorrow." And so I just read it, and it was the 8 classical planets that dominate the system, etc., etc. And I just said, it's just not going to work. No one's going to buy this. And he was gobsmacked. He said, well, this is not possible. The executive have said this. And I said, it'll get voted down because most astronomers are just not going to like the idea of having an infinite number of potential planets. And besides which, most of us think they're Kuiper-Belt objects, these Pluto-like objects. And what's this about having an asteroid stuck in the middle of it all? But interestingly enough, some of you may well know that when Ceres was first discovered, which I think was in 1801, it was classified at the time as a planet. And it was only when a whole pile of other asteroids were discovered that by 1850, it was reclassified as an asteroid. So that's an interesting aspect in itself. So here we go with what we've now got. So this is what they were saying. This is a great diagram in terms of scale, not in terms of distance scale, but in terms of size scale. We have the sun, and again, I apologize to those of you in the room, Mercury, Venus, Earth, Mars, and those on Zoom can see Ceres here. Those in the room will just see nothing, not even a pixel. Jupiter, Saturn, Uranus, Neptune, Pluto and Charon, and even on Zoom you can't see Charon. And then what essentially is Eris sitting at the end here. And so this is a great diagram altogether. So now the IAU, they knew they had a lot of work to do, and they worked very hard. They knew the potential impact, and they made major effort to keep the press on the side, openness, transparency, and everything else like that. And essentially to showcase the process of scientific debate and how things move forward. They had lots of information on the web, Q&A links for the press, public and astronomers, and they set up a press office. And this is Owen Gingerich, who was the chair of the Planet Definition Committee. And so it was all hectic. And so here we come to General Assembly. The first plenary meeting, which is where everyone gets together on the Monday in a big auditorium, the first plenary meeting with everyone in there, this showed this is going to be very, very contentious. And already you could see there's going to be a big negative debate about this. Now, the first meeting of Division 3 was on the 18th. And I normally would never think of going to the Planetary Astronomy Division, but I got there really early, missing one of the active galaxy sessions. And in fact, they were standing room only. I managed to get a seat, but it was actually packed out the door, standing room only. There was lots of quibbles about the executive's definition of plutons and things like that. Pluto and Charon is a double planet. Now, what does this actually mean? They were unique in the solar system, and people were very doubtful about this. Every planet in the solar system.
Hello, Ian.
Yep.
Hello, Ian. Sorry, we lost the connection there. So, so we've lost about 3-4 minutes. If you could take your slides back,
Okay. How many
lost it?
How many
Keep
slides
going.
back?
Keep going. One more. Oh, 2 more. Yeah, that was all. Yes. Yep. You were just talking about the press release and it not being accepted.
Okay, so this. So I think I put the curse in
Sorry
you by
about
saying I just apologize for people in the room. I said it's a fabulous diagram. It's accurate in size but not in distance scale, and the people in the room won't be able to see some of the things. There's Mercury, Venus, Earth, Mars, and then here we have Ceres, and you won't be able to see that. Jupiter, Saturn, Uranus, Neptune, Pluto, and Charon, and then Eris at the end. And the people in the room struggle to usually see these and don't have a chance on the series. So I was saying that the IAU recognized the potential impact, and they made major efforts to keep the press inside the press room, show an open and transparent process of scientific debate with lots of information on the web, Q&A links to the press, public and astronomers. And this essentially is the press room that was going ahead with. So lots of work going on there. And the first plenary meeting where everyone meets together, all a few thousand of you in the very large auditorium, this showed it was going to be very, very contentious indeed. And the first meeting of Division 3, the planetary astronomers, was on the 18th, which I went to missing an AGN, got there really early. And in fact, it was absolutely packed out with standing room only. So this Pluto and Charon, the double planet, unique in the solar system. Now, what do we mean by this? For all the planets in the solar system going out to essentially Neptune, the center of gravity of the planet-moon system is always inside the planet. It's inside Jupiter, it's inside the Earth, it's inside Saturn, it's inside all the others. So all the other planets have their satellites orbiting about them. Charon is so large that the center of gravity between Pluto and Charon lies outside of Pluto, between Pluto and Charon. So Pluto and Charon orbit a common center of mass, which is not inside Pluto and not inside Charon. This makes it essentially a double object or a double planet, as the IU executive would have it. And this made it unique in the solar system, which also caused some concern. And so Division 3 really were very much up in arms about the simplistic view of defining a planet. And they wanted a further point added. A planet must have cleared its orbit. Now this to me, I mean, this was absolutely new. I'd never ever heard of this or thought of this or thought there would be any reason why this is why you had to. But the planetary astronomers who do planetary dynamics, and there are a whole bunch of these people, they're news to me, and they were mostly old and they were all men, but nevertheless, they were people who'd spent their entire lives working on planetary dynamics and orbits, and they were absolutely adamant to be a planet, it must have cleared its orbit. So here we go. There was lots of counter proposals mounted, mainly led by Alan Stern from the New Horizons mission, which was the mission to see the outermost planet in the solar system, Pluto. So he wasn't very pleased if Pluto was going to be demoted from being a planet. He got an email petition together and got 200 names in the space of the week of the conference. And then people said, well, hang on a minute. If you have to have clearing of orbit, doesn't this rule out Neptune? And the answer is there's a whole pile of bodies in Neptune's orbit, and we'll see not only Neptune. And the planetary astronomer said, no. This is all explained by resonances, which we'll get to shortly. And then people said, well, what about Jupiter and the Trojan bodies going before in Jupiter? And the answer is, oh, it's all resonances. And it's all about Lagrangian points and resonances. And so here we have a really good diagram. In the center, we have representation of the sun. And then we have a planetary body, which could be the Earth. In this case, it could be Jupiter. It could be anything else like that. But there are certain orbital positions which are essentially neutral. And if we pick L2, for example, L2 is the second Lagrangian point. And if this is the Earth in blue, so we have the sun and the Earth, then L2 is a position to which many of the observatory satellites go. The Gaia mission, James Webb Space Telescope mission will go there, or it's gone there, is actually out there. And we'll see pictures tonight later on. So L2 essentially is balanced by the gravitational attraction of the Earth and of the sun, although they're both the same direction. And you don't require much thrust to enable a body placed at L2 to remain more or less at L2. And L1 is similar on the inner side. There's also these points L4 and L5. And these are Lagrangian points, which are also stable for trailing and leading bodies of this planet. And if we have a look at what this means, this is now an example of the Trojan, nominally called Trojan asteroids, leading and following Jupiter. So this is an animation of what they look like. And interestingly enough, Lucy is a mission to go and look at the Trojans. October 2021, it launched. It will eventually, by Earth assist gravity, get there in 2027 to the leading bunch. Then it'll come back to the Earth, spin around the Earth, and go back to arrive 2033 to the trailing bunch and essentially investigate two of these bodies. So back to the General Assembly. There's another very, very stormy Division 3 session on the 22nd. People are getting quite rude. And because it was known it was going to be so packed out, it was moved to the main auditorium. So it was really another plenary session almost, because everybody was there. There were lots of very passionate speeches for and against, and I sat there in the audience thinking, this is all good fun, really. The resolutions were being changed in real time. There were amendments being postulated. The chairman, who was the president of the IAU, Ron Eakers, he was clearly losing control. He was being accused of being biased, which of course he was, because the executive had come up with their motion, which didn't have Division 3 in there. So it really was getting very, very fractious. It was getting so fractious that the final plenary session on the 24th, they put Justin Bell Burnell in, essentially to run the show as a neutral observer. And this was the day of the vote. There was lots of comments going on, still confusion on the status of Charon. It was a packed session, but unfortunately, I had to go back to Edinburgh at the time because I had a very important meeting. But I was plugged in on the video because the European Southern Observatory and the IU together, and decided they're going to video this whole session. So I could watch it on the screen as a video. And I also had a colleague in the audience who had a cell phone who was telling me exactly what was going on when you couldn't exactly figure out what was going on from the video. So he was saying, oh, this is going to be really close, this vote. So I missed it, but I was essentially there in spirit. This is Jocelyn with her bits and pieces to try and work their way through the sim. She did a fabulous job. She really did an absolutely fabulous job. And so what was the final resolution? The IUU therefore resolves, therefore resolves. It's very good, that. The planets and other bodies in our solar system, except satellites, be defined into 3 distinct categories in the following way. So here we go. You will see this is very, very similar to what we had before. And I won't read it all out apart from going to part C, has cleared the neighborhood around its orbit. So the executive had taken on board the fact that Division 3 were not going to go away on this, and they got their way in the end. Then we had a dwarf planet definition. And this is where I thought this is a real cop-out. Why don't you just call them TNOs or KBOs? But a dwarf planet is a celestial body that A, is in orbit around the sun, B, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic nearly round shape. C, has not cleared the neighborhood around its orbit, and D, is not a satellite. So I have a whole bundle of these new dwarf planet thingies. All other objects, except satellites orbiting the sun, shall be referred to collectively as small solar system bodies. And I have to say, I've yet to hear anybody call anything a small solar system body, but that's the definition. There are amendments, insert the word classical before planet, which I'll pass over. This is an interesting, Pluto is a dwarf planet by the above definition, is recognized as the prototype of a new category of trans-Neptunian objects, which is a whole big mouthful. At least it recognizes TNOs coming into this, and what to call them Plutonian objects. So then you come to the vote. This essentially is the view from the video that I was looking at in Edinburgh, and people had to hold up their yellow sheets of paper that they were given when they came into the conference hall after declaring their IAU members, because they're also observers who were present at the meeting. And so this was what happened at the meeting altogether, and the results. The resolution, the first one, was passed with overwhelming majority from the audience show of hands. In other words, that was fine. The first amendment went to a vote, 91 votes in favor, but an overwhelming show of hands against. That was adding the word classical, although why they bothered with only 91 votes in favor, I have no idea why they had a vote. The second amendment passed with 237 for, 157 against, and 17 abstentions. This is Pluto is a dwarf planet. So this whole gubbins about dwarf planets came back in again. And the third amendment failed. And after being in various things, 103 versus 186 against, I would call this a total dead heat. Could have gone either way, but nevertheless, it doesn't really matter. And so then there's a big negative reaction from the public. It was clearly, especially in America, an emotional connection with Disney's Pluto, and they felt this wasn't fair, and all the things we'd learned at school that couldn't be that far wrong. Astronomers pointed out this was totally non-democratic. Only 5% of the world astronomers voted, like 400 members out of the 10,000 or whatever. So they said this is totally bad. US astronomers were very upset, A, because the New Horizons team members would have Pluto demoted, and they thought it was a partisan European thing. So there's a wide range of press coverage, and I've only done a little bit of this. So here we have, what is a planet? The debate continues. This is a very, very good article. In fact, many of them are very good articles. The New York Times article there. Nature, round objects, the overall principle of how science works in terms of you should expect people to be unhappy, but science doesn't essentially exist to please people. It works on facts rather than anything else. Then we have New Scientist, down but not out, with a nice little cartoon of Pluto being ejected from the family of planets. And these articles are actually very well written indeed. And then Nature, Pluto, the backlash begins. And Alan Stern's comment, we do not classify objects in astronomy by what they are near, we classify them by their properties, which is why most of us said, yeah, they're Kuiper-Belt objects. You know, so Pluto was. So bit strange that. And then we had this science, which reproduced the lovely picture that I showed earlier on. And that's really some excellent work. Then we had the cartoons. This is the German Meinung, which is opinion. And astronomers thinking, well, this is what I think of you, the IAU. And we can see what that is. And then we had the public protests. And it mainly was size doesn't matter. Protest for Pluto. And I like these. What is this? We're a what? A dwarf planet? Pluto, 1930 to 2006, revolve in peace. And I like this one even more. Pluto, proof that size matters. And so this was the reaction. And the IAU took this on board. And in fact, there are many lessons learned for astronomy in general. So the IAU now has e-voting for contentious issues, particularly those that might impact non-astronomy and other sciences or the general public. An example of this is the recent but less dramatic IA resolution of the Hubble law being recommended as the Hubble-Lemaitre law. Notice it's only recommended as the Hubble-Lemaitre law, recognizing the work that Lemaitre did along with Hubble, essentially in looking at the expansion of the universe and cosmology. Now, as we're getting to the end, let's look at the New Horizons mission. This mission to go and investigate the outermost planet of the solar system, or as we now know, one of the largest Kuiper Belt objects. It was launched in 2006, so it was launched at the same time as the IU General Assembly, but it takes forever to get out there. It took to July 2015 to get to the Pluto system, and it doesn't do things like what other planetary orbiters have been doing by going into orbit around them. It just whizzes past and takes a few pictures in the process, then goes off to search for other Kuiper Belt objects. So here we have from New Horizons the image of Pluto, and it's a fascinating image. There's lots on the web of people who are interested to look at this. It's got a really an amorphous surface. It's got mountain ranges, got plains. It's got rills on the horizon there. And this is also then Charon. And interestingly, if New Horizons also found there a whole pile of more satellites, which I think we get to in a moment. So 4 more moons go around Pluto. They're tiny, tiny objects called Nix, Hydra, Styx, and Kerberos. It has an atmosphere, a very, very thin atmosphere, but retains its atmosphere even when it's at its farthest distance from the sun. This is a view of the atmosphere looking back towards the sun with backlit, which I think is my favorite picture of essentially Pluto, as New Horizons whizzes off into essentially the Kuiper Belt object area. And this is the next thing it took a picture of, which is Arakoth. This is the Native American name for sky. And originally this was called Ultima Thule by NASA, who naughtily said that they could name whatever they saw. And in fact, as we've heard beforehand, they can't. And so because Ultima Thule has some not particularly pleasant connotations as derived from World War II, this was renamed. But the interesting thing is it's clearly 2 objects which have come together and stuck. And this is quite important because it shows you in the outer parts of the solar system, relative velocities can be sufficiently low that bodies will stick and will coagulate together. And therefore you certainly can build up planetary systems by having sufficient density that they won't all smash into each other and cause them fragmentation. In fact, you can get them to collide and stick. This is a very complicated diagram, so don't worry about it. I'm just going to talk my way through it and help you. This on the y-axis, this is the inclination of bodies in the solar system. And on the x-axis is the distance of Saturn, Uranus, Neptune, and then the Plutons, or where Pluto and Charon is, the Kuiper Belt in general, and then where Eris and other bodies are. And this is a scattered disk essentially, but you see they go to very high, and these are where the centaurs are, essentially in the inner part of the solar system. And this was really quite an important aspect because once you start working out where these are, it was first thought that, well, it's thought about the origin of the solar system. When the planets first formed, they formed farther out than they are now. Then they all moved much further in. Then they move back out again to an equilibrium. And by looking at the dynamics of these bodies here, you can actually get clues as to how these bodies, Saturn, Uranus, and Neptune, moved in the early part of the solar system and then migrated outwards. And this was only possible by essentially modern supercomputers and all the observations which allow you to plot on this diagram where things are. The supercomputers can then take all these and work out all the resonances and essentially what would have happened to be able to produce what you've got now by the migration in the early solar system. So it really is a whole new ballpark of new discovery. Final speculation. Is there a 9th planet? Well, the famous Mike Brown of Planets 10 and 11 thinks so. He thinks there's one 6 times the Earth and 15 times farther out than Neptune. He proposed this in 2016 based on essentially the orbits of Sedna and a few other really way out TNOs. Most astronomers don't believe this to exist. They think it's again down to resonances. But people do accept there might be a possibility for a planet in the Oort cloud much, much further out, but also much, much, much bigger. But really don't know. But new telescopes like the LSST, it's on the Vera Rubin telescope, might well be able to shed light on this in the future. And also we have interstellar visitors. Oumuamua essentially appeared suddenly in 2017, this pencil-like artist impression of what it looks like. And this is an interesting thing because it came from interstellar space. It's not from the Kuiper Belt object. It came whizzing into the solar system, as we see here, whizzed in, flashed past the sun, whizzed out with high velocity, and will never come back again. But just shows we can be visited by things from out there. And that then leads to worry about things like this. You'll be aware of the Gaia mission, the satellite that's taking images and spectroscopy of everything in our galaxy. And it's been doing that for now almost 10 years or 8 years at least. It's been looking at star movements, and it's found that Gliese 710, which is a miserably red dwarf star, in 1.3 million years, it actually will cross through the Oort cloud of our solar system. And in so doing, there's certainly a possibility for sending comets or asteroid cometary bodies into the inner solar system. And could that be an extinction level event? And so if we're around in 1.3 million years, we might need to worry about, okay, how can we sort of deflect these comets? So with that, we'll call it quits. Thank you very much.